the two most common and simplest forms of data that we're required to work with on a daily basis are strings and numerical data. Java provides the java.lang.math class, which provides us with a very large number of useful static methods. But it's also important to recall the basic primitive types that we use for representing numeric amounts. And in particular, as we discussed yesterday, there's a need to convert between different numeric types. So for example, we might have a double, which is 3.142, which if you remember your basic maths, is equal to the value of pi, or at least to a few digits. Now, if we want to assign that double value to an int, we're going to have a bit of a problem, because those different primitive types are not actually assignable to each other. But if we use our old friend alt-enter to show possible ways to resolve it, we can use a cast, which essentially will cut off the decimal part and just return us with an integer number. Before we start looking at some of the methods in Java Lang Math, let's take a couple of minutes to talk about one other aspect of Java's maths which comes in surprisingly useful. This is the subject known as modular arithmetic. And in fact, it's a form of arithmetic that you're probably already familiar with, although you may not know it by that name. It's the arithmetic of the clock. A clock does a complete revolution every 12 hours. So 1300 hours is otherwise known as 1 p.m. So 1 and 13 are the same number. Java has a natural way of supporting this style of arithmetic, and it uses a little operator, the percent sign. So how does this work? Well, first of all, let's give I a nice clean value, just so that it's easy to understand. Let's give it, for example, the value 17. Now, if we take a system out println, 17 is a good number because it's actually a prime number, and it means that we can, for example, if I use 5. Now imagine a clock face which only has 5 numbers on it rather than the usual 12. Every time we sweep round a complete revolution, we've gone round by 5 times. So if we start with a number like 17, and you imagine counting down by 5 each time. So you count down once, and you get down to 12. 12 is still bigger than 5, so you count down again, and you get to 7. 7 is still bigger than 5, so you count down again by 5. And you end up, ultimately, I hope, with 2. And sure enough, that's right. So a more familiar example perhaps is, so let's do that with 12, because that's actually like a clock. And 1700 hours is actually 5 in the afternoon. And so, as you can see, by using the modulus operator, the modular arithmetic, we count down from 17, which is bigger than 12, so we count down by 12, and what's left over is 5. It might seem a slightly odd and slightly quirky thing to be built into the basic language, but it's amazing how useful this technique can be when we're working with real data. Let's move on and start to look at some of the methods in Java Lang Math. Like many parts of the Java Standard Library, the math class contains many helpful static methods which can be used for a surprising variety of the basic tasks that we need for working with numbers. It's always helpful to remember Java's primitive types, particularly double and float. Now, these days, for most mathematical operations, if you need floating point numbers, or decimals as you might think of them, you should pretty much always use double. Float really has limited applicability, and I think these days, if we were designing the language from scratch, we probably wouldn't have included float as a type. So if we look through all these static methods, and as you can see here from the Java doc, virtually all of them have static on them. So we're talking about methods that may be familiar if you were awake during your trigonometry classes at school. So we can find things like Well, there's the cos method. And of course that will return you the cosine. And if we dig around, we can probably find a sine method as well. There are also useful methods, for example, the max method, where if you pass it two integers, you can return the greater. So let's just see that in action. Let's get rid of some of this old code. Arrange for a print statement, and let's do math.max, and let's give it, let's say, 4 and 7. And that should hopefully print 7 on the last line, and sure enough it does. Let's get rid of some of these other string bits, string code up there. And what else might we want to do? Well, there's the power method, which returns one number to the power of another. So let's say 2 to the power 10, which, providing I've done my sums correctly, that should come back with 1024. Ah, no, and it doesn't, because I've actually forgotten to change the method. So let's try that again. This is why it's important to test your code. And there we go. And as you can see, that's come back with 1024, but it's actually got a 0.0 on the end. Now, you might ask yourself, why is that the case? But if we come back to the Java doc, it should be immediately apparent. Because although I've passed it in integers, ints in this case, it's actually expecting doubles. So on the way in, those two ints have been silently converted into doubles, and the method is actually also returning a double. So because of that, this is the telltale sign that in the output, you see, we have this point naught at the end. And that's typically a sign that we're returning a floating point number, in this case a double. One of the other interesting and important methods is random. And what this does is it returns a random number. The standard says between 0 and 1. So let's take a look at that and let's play with some numbers. And let's use our old friend from earlier on, the for loop. So what do you think? Let's print out, let's say, 40 random numbers between 0 and 1. Yes, and the ID is complaining about the fact that I haven't actually declared my variable. So remember that even when you're using a for loop, you have to always make sure that the variable's been declared, and we've told Java what type it is. So let's run that. Yeah, there we go. There's sort of 40 random numbers there between 0 and 1. Okay. Now, sometimes people don't always understand what is meant by a random number on a computer, and I think it's worth just taking a couple of minutes to talk about that now. See, computers can't really produce genuinely random numbers. We know that in nature, random numbers do exist, quantum fluctuations and so forth. But a computer can't do that. Instead of which, what they actually use is a system of linear algebra, of simple linear equations, to generate a sequence of numbers which looks random. And then they use some basic inputs from the computer itself, such as the system clock or some activity by the mouse, to determine where in that sequence to start. Ultimately, over time, the numbers which are generated will repeat themselves. And once they've started to repeat themselves, they will carry on in the same sequence that they did last time. So these aren't really random numbers. They're sometimes called pseudo-random numbers, or PNRG, for the generating functions which are used to generate them. But for all intents and purposes, unless you're doing heavy cryptography or you have a statistician who needs a very high source of random numbers for your models, for most working programmers, the functions which are presented in Java Lang Math Random, or indeed in some of the Apache libraries and other third-party libraries which provide random numbers, for practical purposes, they're going to be good enough for most applications. We've only scratched the surface of Java's capabilities to handle numbers and numeric data. However, we must move on. But before we do so, let's take a couple of minutes to look at Java's parsing capabilities. This basically starts from us having a string which we believe represents a number and turning it into an actual number. The methods for these aren't actually contained on the math class. Instead, they're on the individual classes called integer and long and things like that. So let's take a look at these. Now, up until now, we haven't really talked about the class called integer. You've seen int, the primitive type, which is present in blue in the IDE. Integer is a proper class, but it's effectively almost the mirror or the grown-up version of int, which is itself a proper Java class type. And Java has ways of automatically converting between int, the primitive type, and its pair, its opposite number, integer, the class type. So let's have a quick look at that. And the way that we would do this is we can... And this seems slightly strange or perhaps even baffling at first glance, because as we talked about in earlier sections, Java is a statically typed language, and it seems very strange that we should be able to put 3, the value, the primitive type, into something which is clearly a reference type. I mean, there's the class integer. We can see that it's in black in the IDE. We know that it's actually a proper class type. So what's actually happening? Well, this is really just a convenient shorthand. Under the hood, Java is really writing code like this. So what we're saying is that the value 3 is being boxed into a class type. So the class type, known as integer, represents, in an object-orientated way, the simple type int. So each primitive type has a corresponding pair which is a class type. Int has integer. Boolean has capital Boolean. But because we want to save ourselves some typing, the Java compiler actually understands that when we write an expression like that, or like this, that we know what is meant. Because the only way that that expression would make sense is if a new object is being created which holds that primitive value inside of it. So this type of boxing exists, and we can, of course, also go the other way, where if we, for example, require a primitive int value, but we have an integer object, that Java understands that it will be automatically converted where necessary. So that's where this class integer comes from. If we look at the methods that are on it, there are a couple in particular that are worth calling out, notably the parseInt method. Notice that this is a static method. So if we just get rid of some of this. Integer.parseInt. And let's suppose we've got a number like 42 in there. And it actually is parseInt. There we go. And you can see that what's happening is we're taking the string 42, we're parsing it, we're turning it into an int, but then we're just printing it straight back out again. So you think, well, what's the point in that? We might as well just have printed out the original string. But the point is that this is a genuine int. So what do you think might happen if we run this? I claim that it's actually going to print 43. And sure enough, it does. Because we're generating the int 42 from the string, we're adding 1 to it, and then we're printing out the result. So if, for example, we have 5 added to that, that should now be 47, and so forth. Now, what happens if I just mangle some text in there? What do we think might happen? Well, actually, there you go. What we actually get is an exception. So we've met these before briefly in other sections. This one's actually a number format exception because it turns out when you have the string 42 and then just mash on the keyboard that actually that doesn't produce you a good number that you can actually use. Who would have thought that? So in real code, when you're actually trying to parse input for things which should be numbers, but which aren't necessarily. It turns out you actually have to wrap them in a try-catch block. So yes, to be completely safe, what you do is you set up an I0 like that. Put this in a catch block. Control-Shift-F, reformat the code, and let's run that and see what we get. You see, because I've set our I up to be 0, if it turns out this string is bad, actually I remains as 0. Actually helps if the code actually does try to reassign to I. There you go, that's 47. But if I just mash on the keyboard sum, then that should just be 5. And sure enough it is.